If you go deeper into anything, then you'll definitely find maths in everything. So is it really important to learn maths now? Yes, of course it is important. So now let us learn chapter 1 of class 9, real numbers. This would be an introductory video where I would explain you the concepts of this chapter, and problems will solve in the later videos. So now let's get started. In this video we are going to deal with these concepts. In your earlier classes you have already learned about natural numbers, whole numbers, integers and rational numbers. Now in this class let us learn about real numbers. Before that, let us firstly revise what we have learnt in the earlier classes. So now, what are natural numbers? For instance, if I ask you to count the number of stars in the sky, then how do you start counting? You start counting by saying 1, 2, 3 and so on, and you say that there are so many stars in the sky. Okay, you can try counting and the number continues. So it is, you start counting by saying 1, 2, 3 and this continues. Yes, so there are endless number of stars in the sky. Yes, the same thing we can represent it by this symbol. It is called infinity. Okay, infinity means there is no end to the numbers. The numbers can be as large as they can. Okay, and now this set of numbers, as we have already learned, they are called as natural numbers. Okay, so the numbers starting from 1, 2, 3 and so on till infinity, this set of numbers are called natural numbers. And also these numbers are called as counting numbers. Why? Since whenever you try to count, you start your count by saying 1, 2, 3, isn't it? So these numbers are called natural numbers as well as counting numbers. Now let us see what are whole numbers. Now if I add a number 0 to this set of natural numbers, then this is called as whole numbers. Yes, 0 is a very important number which we use very frequently, right or wrong? Suppose your mother has given you 100 rupees and you have spent all the 100 rupees in buying something. So if I ask you how much money is left with you right now, so what is the answer? Your answer is 0. Yes, so 0 is very frequent used, and if we add this 0 to the set of natural numbers, then what do we get? We get whole numbers. Clear? Now we also need negative numbers along with these numbers, yes or no? So for example, if I have to measure temperature, now we say the temperature is minus 10 degrees centigrade in Chicago. Yes, now what is this minus 10 degrees centigrade? So minus 10 is a negative number. Yes, so if we add negative numbers to this set of numbers, then we get integers. Okay, so negative numbers also, they are till minus infinity. Okay, so it continues. So for example, it is minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on till this is plus infinity and this is minus infinity. Okay, now this set of numbers is called as integers. This is what we have already learned. Now suppose your teacher has awarded you marks, say 18 out of 20. These are the marks you got in English. Now you got 20 out of 20 in science and 19 out of 20 in maths. Now what are all these numbers? These numbers are of the form P by Q. Okay, and where this is P and this is Q, so P and Q both belong to integers, and the other condition for this is Q is not equal to 0. Yes, now such a number, then you can call these numbers as rational numbers. Clear? So rational numbers are numbers which are in the form of P by Q, where P and Q belongs to integers and Q should not be equal to 0. Then these numbers are called rational numbers. Can you give me some more examples of rational numbers? For example, 169 by 240 is a rational number. It is in the form of P by Q. And 21984 divided by 116 is a rational number. Yes. Now is 20 a rational number? Yes, it is, because 20 can be written as 20 by 1. Yes, which is in the form of P by Q. Yes, is 15 a rational number? Yes, it is, because 15 also can be written in the form of 15 by 1, which is in the form of P by Q. Now tell me, is minus 3 a rational number? Yes, it is, because minus 3 can be written as minus 3 by 1, okay, minus 3 divided by 1, which is in the form of p by q, where p is minus 3, it is an integer, q is 1, which is also an integer. Yes, so now all these are nothing but, now this 20 is a natural number, 20 is a whole number also, 15 is a natural number, it is a whole number as well. Now minus 3 is an integer, yes, this is an integer, this is a whole number as well as natural number, this is natural number as well as whole number. So you can see that natural numbers can be written in the form of rational numbers, whole numbers also can be written in the form of rational numbers, and integers can also be written in the form of rational numbers. So generally we can conclude and say that natural numbers, whole numbers and integers are a part of rational numbers. Do you agree? So now, as you already know, natural numbers are represented by capital N, whole numbers are represented by capital W, and integers are represented by capital Z. Okay, and rational numbers are represented by capital Q. Okay, so now we can say that natural numbers are a subset of whole numbers. Yes, you can see that natural numbers are nothing but a part of whole numbers. This is nothing but natural number set. Yes, so 0 added to natural numbers gives you whole numbers. So you can say that natural numbers are a part of whole numbers. That is the same thing which we are representing here. Natural numbers is a subset of whole numbers. Okay, and also you can say that whole number is a subset of integers. Now here you can see, from here it is whole number set. Yes, so whole numbers are just a part of integers. Yes, so you can say that whole numbers are subset of integers. And now, as I have already explained you, integers are again a part of rational numbers. Every integer can be written in the form of rational numbers. So integers are a subset of rational numbers, or they are part of rational numbers. So this is the generalized form which you can write, that natural numbers are subset of whole numbers are subset of integers, and integers are subset of rational numbers. And rational numbers can be written in the form of p by q, where p and q both belong to integers, and the condition is q should not be equal to 0. Now what happens if q is equal to 0? So let us take an example, say 5 by 0. Okay, now here p is 5 and q is 0. Now if q is equal to 0, what happens to the division? You cannot divide any number with 0. Why? Suppose if I have 5 chocolates and if I want to divide among 0 people, how will I divide? The division is pointless. Yes, so here also the division is pointless. You cannot divide a number by 0, because when there is nothing, when there is no one here to divide, to distribute the chocolates, to whom will I distribute? So the question itself is pointless. So here also the question itself, you want to divide 5 among 0. What is 0 here? So this is pointless. So the division is pointless. So that is the reason why q should not be equal to 0. Why? If q is equal to 0, then the division is pointless. So we take the condition that q should not be equal to 0. P and q should be integers. Now let us move to the next concept. Now that we have learned about natural numbers, whole numbers, integers and rational numbers, let us see how to represent them on the number line. So what is the number line? You have already learned in your earlier classes. So firstly you draw a line, and if I want to represent natural numbers on this number line, then I start marking from number 1, because natural number starts from number 1. Yes, so with a unit distance we mark number 2, and again with a unit distance we mark number 3, and so on. Yes, now to the same number line, if I add 0, okay, now this number line is nothing but it is whole numbers number line. Okay, this represents whole numbers number line. Now for the same number line, if I want to add negative integers, then just add -1, -2 and so on with a unit distance. Now unit distance is nothing but from one number to the other number you have a fixed distance, you maintain a fixed distance. Now this fixed distance is called as unit distance. Okay, so 0 to 1 it is unit distance, 1 to 2 also it is unit distance. Okay, at equal distances you mark the numbers. So now as you can see, this is integers number line. Now you have also learned how to mark rational numbers on number line. Yes, for example, if I want to mark 1 by 2 on the number line, how did we do that? So you take a number line, Okay, now 1 by 2 is simply a proper fraction because the numerator is less than denominator. Do you agree? So now it is between 0 and 1. Always a proper fraction is between 0 and 1. It is less than 1. Yes. So mark 0 and 1 on the number line. Okay. Now the denominator tells you how many parts should you divide the unit distance. Okay. It tells how many parts the unit distance has to be divided. So it is 2 here. Denominator is 2. So this unit distance has to be divided into 2 equal parts. Okay, so now this is the 2 equal parts. So this is part 1 and this is part 2. Clear? Now the numerator tells how many parts should you take it into consideration. Now numerator is 1, that means you have to take 1 part into consideration. So this is nothing but 1 by 2. Okay, let me take another example. Now if I have to represent 2 by 3 on the number line, okay, 2 by 3. Now here also you can see that numerator is less than denominator, so it is a proper fraction and the value lies between 0 and 1. Clear? So now drawing the number line, okay, marking point 0, 1, 2 and so on. Now the denominator tells you into how many parts should the unit distance be divided into. Okay, so denominator is 3, which means that you have to divide this unit distance into how many parts? 3 parts. Okay, so it is 1, 2 and that is the third part. Okay, so this is part 1, part 2 and part 3. Clear? Now the numerator tells you how many parts should you take it into consideration. Numerator is 2, that means you have to take 2 parts into consideration. So it is first part and second part. So this is nothing but 2 by 3. Now the same thing, if you want to mark minus 2 by 3 on the number line, then how do you do that? Nothing but you will consider the negative integers. Okay, now this is 0, which means if you mark minus 1 at a unit distance, now this would be minus 1. Yes, so now you have to divide the distance between 0 and 1 into how many divisions? 3 divisions. Okay, so it is 1, 2 and this is the third division. So 1, 2 and 3. Okay, since this is a negative fraction, we are considering the negative side. Okay, the negative integer side. Clear? So now the numerator tells you how many parts you have to take it into consideration. Numerator is 2, so you have to take 2 parts into consideration. So this is first part and this is second part. So this is nothing but minus 2 by 3. Clear? Now let us take another example. Suppose if you want to mark 5 by 3 on the number line, then how do you do that? So if you see here, numerator is greater than denominator. Yes, 5 is greater than 3, which means this is an improper fraction, which means that the value is greater than 1. Till here we have seen that the value is always less than 1. Since it is a proper fraction, here it is an improper fraction, the value is greater than 1. So how do you do it? You can do it by simple division. Okay, so 5 divided by 3, so 3 ones are 3, subtracting you get 2 as a remainder. So 5 by 3 can be written as 1, 2 by 3. Yes, 5 by 3 is an improper fraction. You can convert it into mixed fraction as 1, 2 by 3. Okay, so quotient, remainder and the divisor. Clear? So now you can draw the number line and mark 0, 1, 2, 3, okay, at unit distance from each other. Okay, each number is at unit distance from each other. Now 5 by 3 is nothing but 1, 2 by 3. Okay, the integral part is 1, which means this value lies somewhere between 1 and 2. Yes, so it is between 1 and 2. Okay, now if you look here, it is 2 by 3, which means the value between 1 and 2, the unit distance between 1 and 2 has to be divided into how many parts? 3 parts. The denominator is 3, so you have to divide between 1 to 2 into 3 parts. So 1, 2 and this is the third part. Clear? So this is part 1, part 2 and part 3. Clear? Now how many parts should you consider? 2 parts. Okay, numerator tells you how many parts you have to consider. 2 parts. So it is first part, second part. Now this is nothing but 1, 2 by 3. Okay, and 1, 2 by 3 is nothing but 5 by 3. Clear? So this is one way of marking 5 by 3 on the number line. Firstly, you will convert it into mixed fraction. Now after converting this into mixed fraction, this integral part tells you between which two numbers does this rational number belong to. Okay, here the integral part is 1, which means this number lies between 1 and 2. Now let us see the second way how we can mark 5 by 3 on this number line. So what can be done? We can draw a number line, okay, marking 0, 1, 2, 3 and so on. Okay, now without converting into mixed fraction, you will just consider 5 by 3 as a whole. Okay, so marking 5 by 3, how do you do it? Now the denominator is what? 3. Okay, so you start from 0. Okay, from 0 to 1 you divide it into 3 parts. Again from 1 to 2 you divide it into 3 parts. Okay, again from 2 to 3 also you divide it into 3 parts. Okay, since the denominator is 3, you divide each of the unit distance into 3 parts. Clear? So this is first, second and third part. First, second and third part. Okay, so let me mark here so that it will be clear for you. This is part 1, 2 and 3. This is 1, 2 and 3. Clear? So now how many parts should you consider? The numerator tells you how many parts you have to consider. Numerator is what here in this case it is 5. So you have to consider 5 parts from the beginning. Okay, so this is part 1, 2, 3, 4 and 5. So this is nothing but 5 by 3. Clear? So you can do in any of these two ways. Clear? Whichever is comfortable for you. You can either convert this into mixed fraction and check between which two numbers does this fraction lie. Okay, so now here the integral part is 1, so this fraction is between 1 and 2. Okay, now you will divide only this distance between 1 and 2 into 3 parts and you will take the required number. Otherwise, you can start from 0, you can divide it into the required number of equal parts. Here in this case it is 3. Unit distance is divided into 3 equal parts. Okay, so you can divide each of the unit distance into 3 equal parts and numerator gives you the number of parts which you have to take into consideration. Here it is 5. So start counting from 0. Okay, now this is first part, second part, third, fourth and fifth part. So you start from the 0 and you take the fifth part. Clear? So you can use any of the two ways, and this is how you can represent rational numbers on the number line. Now let us see how can we insert numbers between any two numbers. Okay, now suppose if there are two numbers 3 and 5. Can I insert any natural number between 3 and 5? Yes, I can. Between 3 and 5 you have a natural number 4. Yes. Now if there is a number minus 2 and 0, can we insert any integers between minus 2 and 0? Yes, we can. So between minus 2 and 0 you have minus 1. Yes. So now can I insert any integers between 3 and 4? No, we can't, because 3 and 4 are immediate integers. Okay, successive integers. The very next integer after 3 is 4. So you cannot insert any more integers in between these two integers. Yes, but can I insert a rational number between 3 and 4? Yes, we can. Now we already learned that 3 is an integer as well as it can be called as a rational number too. Why? 3 can be written in the form of 3 by 1. 4 also can be written in the form of 4 by 1, and we have learned that integers are a subset of rational numbers. Yes, so all the integers, they also belong to rational numbers. Yes, so now we can insert rational number between these two rational numbers. So instead of calling them integers, I am calling them rational numbers now because they belong to rational numbers also. So now I want to insert a rational number between 3 and 4. How do I do it? The method which we have learnt in our earlier classes is mean method. Yes, nothing but we can take average of both these numbers. Yes, so how do you do that? You simply write 3 plus 4 by 2. Okay, adding both the numbers and dividing it by 2. So you get the answer 7 by 2. Clear? Now 7 by 2 is a number, a rational number between 3 and 4. Okay, so if you draw this number line and if you want to mark 3 and 4 on the number line, now this 7 by 2 is exactly in between 3 and 4. Yes, now if I want to find a rational number between these two numbers, How can I do that? Using the same mean method, you can just take the average of these two rational numbers to find the rational number between these two. Yes, so 3 plus 7 by 2 whole divided by 2 gives you this rational number. Okay, so let us see what it is. Now taking LCM, it is 6 plus 7 by 2 and you have another 2 in the denominator. Okay, so this is nothing but 13 by 4. Now 13 by 4 is a rational number between 3 and 7 by 2. Yes, similarly you can find a rational number between 7 by 2 and 4. Yes, using the same mean method. Also you can find rational number between 3 and 13 by 4. Yes, so in this way we can find infinitely many rational numbers between any two rational numbers. Now let us see another method. How can we insert large number of rational numbers between any two rational numbers? Now for example, if I want to insert 5 rational numbers between 5 and 6. Okay, how do I do it? Now 5 and 6 are rational numbers because they can be written in the form of P by Q. Yes, 5 by 1 and 6 by 1. Yes, so they are rational numbers. Now if I want to insert 5 rational numbers between these two rational numbers, using mean method I have to take number of times, number of steps are needed and it is a lengthy process. Yes, you have to find the mean of 5 and 6. Again you get an answer like this. Again you have to find the mean of 5 and the answer which you get. Yes, so this process continues. Instead there is one step process where you can find 5 rational numbers between these two rational numbers. How? So since you want to find 5 rational numbers, you will multiply both the numerator and denominator with a number more than the required number of rational numbers. Okay, so required number of rational numbers here are 5. Yes, required number is 5. You want to insert 5 rational numbers between these two. Yes, but you will multiply with 6. Okay, you will multiply with 1 more than 5. Okay, with 1 more than the required number of rational numbers. Okay, for example, if I want to insert 10 rational numbers, then with what number will you multiply? You will multiply with 11. Okay, so always you will multiply with 1 more than the required number of rational numbers. This is clear for you? Now 5 can be written as 5 by 1 and 6 can be written as 6 by 1. Yes, now as I said, since we want 5 rational numbers between these two numbers, now you will multiply by what? By 6. Both the numerator as well as denominator you are going to multiply by 6. Okay. Now if you see, this is nothing but 5 6 are 30 by 1 6 are 6. Now 6 6 are 36 by 1 6 are 6. Clear? So now you can see that after 30 you can insert 31 here. Yes, so let us insert. So 31 by 6, 32 by 6, 33 by 6, 34 by 6 and 35 by 6. Now this is 36 by 6. So you can see that 1, 2, 3, 4, 5 rational numbers we are able to insert between any two numbers. Yes. So simply you have to see the required number of rational numbers and you have to multiply the numerator as well as the denominator with one number more than the required number of rational numbers to insert the rational numbers. Clear? So now this is when you have same denominators. Now what if we have a different denominator? Let us see. Now here 5 is written as 5 by 1, 6 is written as 6 by 1, which means both are like fractions, both have the same denominators. Now if a question is given to you where you have different denominators, what do? Suppose if you have 1 by 2 and 2 by 3 and you have to insert 10 rational numbers between these two numbers, then how do you do it? So firstly you will equate the denominators. Okay, so that means you will convert these fractions. Now these are unlike fractions, you will convert these unlike fractions into like fractions. How? Let us see. So 1 by 2 can be multiplied with 3. Okay, multiplied with 3 both on the numerator and denominator, and 2 by 3 can also be multiplied with 2 both on the numerator and denominator. Now why did we do this? Because 2 3s are 6 and 3 2s are 6. Here we are able to equate the denominator if we multiply the first term by 3 and second term by 2. So our aim is to bring both the denominators as a common denominator. Okay, we want like fractions. That That means the denominator has to be same. So that is what we are doing here. Now 1 3s are 3 divided by 2 3s are 6, and here 2 2s are 4 divided by 3 2s are 6. Now you can see that the denominators are same. Yes, now it is easy for us to insert rational numbers. Now what are the number of required rational numbers which we have to insert between these two rational numbers? It is nothing but we have to insert 10 rational numbers between these two rational numbers. Yes, which means that I have to multiply with one more than the required number of rational numbers. So the required number is 10, so you will multiply with one more than the required number. So 3 by 6 into one more than the required number is 11. Yes, so you multiply and divide by 11, and also 4 by 6 you multiply and divide by 11. Clear? So now 3 11s is 33 by 6 11s is 66, and 4 11s is 44 by 6 11s is 66. Okay, so now you can see that after 33 there is no 34, you can insert it here. So it is 34 by 66, 35 by 66, 36 by 66, 37 by 66, 38 by 66, 39 by 66, 40 by 66, 41 by 66, 42 by 66, 43 by 66, and you have 44 by 66 here. Yes, so just count this 1 2 3 4 5 6 7 8 9 and 10. So easily you are able to insert 10 rational numbers between the given two rational numbers. So firstly you will convert them into like fractions, and then you will follow the same procedure. Okay, you will multiply and divide by one more than the required number of rational numbers. Now let us see how can we convert a rational number into a decimal form. Okay, so let us take an example, 25 by 4. Clear? So now 25 divided by 4. Yes, so we know that 4 6 are 24, and subtracting you get a remainder 1 which is less than 4. So you cannot continue your division. Now what do? You put a decimal point both in the quotient as well as in the dividend. Okay, so since you have placed a decimal point here, you are free to write a 0. Okay, so now bring the 0 down. So now it is 10. Okay, now 10 you can divide it by 4. You know that 4 2s are 8. Okay, again subtracting, you are left out with 2. Clear? Again 2 is less than 4. Since you have already placed a decimal point, you can write a 0 again. Clear? Now bringing this 0 down, now this is 20. Okay, now 4 5s are 20, and the remainder is 0. Yes, so here you can see that 25 by 4 I have converted and I have brought it into decimal form, and it is nothing but 6.25. Clear? Now let us take another example, 25 by 3. Okay, so now if you want to divide the same 25 by 3, okay, how do you do it? 3 8s are 24. Yes, subtracting you have a remainder 1 which is less than 3. So you have to take a decimal point both in the quotient and dividend, the same process. Yes, since you took a decimal point, you can take a 0 here. Now bringing the 0 down, now this is 10. Yes, now 3 3s are 9. Again subtracting you have a remainder 1. So again you can write a 0 here. Since already you have taken a decimal point, you can write a 0 here. So bringing it down, this is again 10. So again it is 3 3s are 9. Again the remainder is 1. Yes, again if you take a 0 and if you divide, again you will get the same remainder and the same quotient 3. Yes, so this continues, and here also the remainder is continuing. Yes, so 25 by 3 I can write it as 8.333 and so on, which is nothing but 8.3 bar. This is what you have learnt in your 8th class. Yes, so this example which we have taken, we have converted a rational number into decimal form, and this decimal form is nothing but terminating decimal. Do you agree? And do you remember this? This is called terminating decimal because the decimal is stopping here. Yes, there is an end to the division. The remainder is 0. There is an end to it, and the decimal is stopping. So this is called terminating decimal. There is fixed number of decimal places here. Yes, you can count. There are finite number of decimal places. In this case, there are 2 places, 1 and 2. Yes, but this is called non-terminating decimal. Okay, that means there is no end to this decimal. Okay, how many ever times you divide it, the quotient continues and the remainder, the same remainder 1, it continues. Yes, so this quotient keeps repeating, this 333 keeps repeating. So you can write it as 8.3 bar. This bar represents that 3 is repeating. Yes, so now here we have also learnt about the concept of period and periodicity in your 8th class. Do you remember? So what is period? Period is nothing but the set of digit which is repeating. Okay, here which digit is repeating? 3 is the digit which is repeating. So period is 3. Now periodicity is nothing but the number of digits which are repeating. Okay, how many digits are repeating here? Only one digit is repeating, so periodicity is 1. Now let us take another example. Suppose 127.753 bar. Okay, now the bar is over 753, which means 753. All the 3 digits are repeating in the same order. Yes, 753, 753, 753 and so on. So let me find the period in this case. Here what are the digits which are repeating? 753 are the digits which are repeating. So period is 753. Now what is periodicity? How many digits are repeating here? 1, 2, 3. 3 digits are repeating. So periodicity is 3. Now I hope this is clear for you and you have got a quick revision of the concepts. Now the rational number, this is the rational number, you were able to convert it into either terminating decimal or non-terminating. Now this is nothing but non-terminating recurring decimal. Do you agree? Why it is recurring? Recurring is nothing but repeating. Again and again you are getting the same number. Yes, it is repeating. You have a bar on it, which means it is repeating. Here also 753 has a bar on it, which means this is also repeating. Now I'll take another example, 82.172 bar. Okay, now here this bar is only over 7 and 2. It is not on 1. Okay, this bar is only on 7 and 2, which means 7 2 is repeating. Yes, now what is the period here? Period is 7 2. Okay, period is a set of digits which are repeating. It is 7 2. And what is the periodicity? Periodicity is 2. Clear? Now here you can see that you have a decimal place which is not repeating. Here one is not repeating. Yes, and you have a decimal place which are repeating. So you have something which is not repeating and something which is repeating. So you have a mixed type of decimal here. Okay, so this is mixed type of decimal. So this type of decimals are called as mixed recurring decimal. Okay, in non-terminating decimal you have 2 types. Okay, it is recurring and mixed recurring decimal. Okay, so this is example of recurring and this is also example of recurring, and this is example of mixed recurring, where you have a decimal place which is not repeating and you have decimal places which are repeating. So it is a mixed recurring. Okay, so you have seen that a rational number can be converted into a terminating decimal or it can be converted into non-terminating recurring decimal or non-terminating mixed recurring decimal. Now keep these points in your mind and let us use these points, these conclusions in our next concept. Now we have seen that rational numbers are either terminating decimals or non-terminating decimals, and if they are non-terminating decimals, they are either mixed recurring or recurring decimals. Yes, what if I give you a decimal number, for example 129.13541782813817 and so on. Yes, now if you look at this decimal number, you can see that these decimal places are non-terminating. Yes, there is no end to the decimal places. Yes, but at the same time you can see that there is no repeating decimal here. Yes, there is no pattern. Now you can see that 1354178628138157. So you can see 13 and 13 is repeating, but after 13 you have 54 here and it is 8157 and so on. So there is no fixed pattern in this. There is no recurring decimals in this. Okay, so you have seen that rational numbers which are of the form P by Q can be written as terminating or non-terminating, and if it is non-terminating it should be either mixed recurring or recurring. But here you see that it is non-terminating but it is non-recurring. Okay, so this decimal number is non-terminating as well as it is non-recurring. Okay, so it is non-recurring. recurring. So you cannot say that this is a rational number. This can be written in the form of a rational number. You cannot say that because this is not a recurring decimal or a mixed recurring. It is non-terminating, non-recurring. So these type of numbers which are non-terminating and non-recurring, these are called as irrational numbers. Okay, so these numbers which are non-terminating and non-recurring, they are called as irrational numbers, and they cannot be represented in the form of P by Q. Okay, we have seen that rational numbers can be represented in the form of P by Q, but irrational numbers cannot be represented in the form of P by Q. Okay, and they are non-terminating and non-recurring. Now let us see few examples of irrational numbers. Now these are the examples of irrational numbers. Okay, you can see that root 2, the value of root 2 is 1.4142356 and so on. So this is non-terminating as well as it is non-recurring decimal. Okay, so you can say that root 2 is irrational number. It cannot be expressed in the form of P by Q. Also the value of root 3 is 1.7320 and so on. It is also non-terminating and non-recurring. So the value of root 2, you know that you can find it in the form of long division method. Okay, using long division method you can find the value of root 2, and the value it just continues. There is no end to it. Root 3 also similarly you can find the value using long division, and the value it also continues. Yes, so root 2, root 3, root 5, all these are examples of irrational numbers. Okay, so in simple words, if you can say, the numbers which are not perfect squares are called irrational numbers. For example, root 1 is 1. Yes, root 2, the value is this, so it is an irrational number. Yes, now root 3, the value is, you know, it is also an irrational number. Now what is root 4? Root 4 is nothing but 2. So 4 is a perfect square number. Yes, and root 5 is again a irrational number. You don't get a terminating decimal or you don't get a recurring decimal here. And again root 6 is also irrational because there also 6 is not a perfect square number. You cannot get a recurring decimal here. Again root 7 is also irrational because here also you cannot get a recurring decimal. And root 8 is also irrational. Root 9, now what is root 9? Root 9 is nothing but 3. Okay, so again root 10 is again irrational. So you can see that root 4, root 3, these two are nothing but perfect squares. Yes, you can find out the square root of this number. Okay, root 4, root 9, similarly root 16, root 25, all these are perfect squares where you can find out the square root of these numbers. Yes, so other than these numbers, all the other numbers like root 2, root 3, root 5, all these are called irrational numbers where they cannot be expressed in the form of P by Q, they cannot be expressed in the form of P by Q, and they are not terminating nor they are recurring. Now Pythagoras found that root 2 is a irrational number, and later on Theodorus found that root 3, root 5, root 6 and so on are also irrational numbers. Now we have learned that natural numbers is a subset of whole numbers is a subset of integers, and integers are subset of rational numbers. Yes, so rational numbers contains all these numbers, natural, whole as well as integers. Now the combination of rational numbers along with irrational numbers, we are saying that a number which is not rational is irrational. So the combination of rational along with irrational gives you real numbers. Okay, so this completes the set of numbers. So real numbers are nothing but a combination of rational numbers as well as irrational numbers. Now in our next class, let us see how can we represent irrational numbers also on a number line. It's your time to check your understanding with do it yourself. So convert 2 by 7 into decimal form. This is a rational number, you have to convert it into decimal form. Also convert 1.732 into rational form and convert 8.73 bar into rational form. This model I have not discussed in this video, but still you have learnt in your 8th class, and if you have any doubts you can refer to class 8 chapter 1 video. I have explained it clearly there. So do it yourself and don't forget to mention your answers in the comment section below. I am very much sure that you have got complete revision of your chapter 1 of class 8, and your chapter 1 of class 8 is very much related to this chapter of real numbers. Already it is a lengthy video and we shall discuss the remaining concepts in the next part. If you like this video, give this video a big thumbs up and tell me how did you like this video in the comment section below, and also share this video with all your friends. You can also follow me on any social media network. The links I am giving you in the description box below, and also you can ask me any query, any doubt or any help regarding your subject in the comment section below or in any social media network. And don't forget to subscribe, because subscription is free of cost, and you also get your worksheets for free of cost if you text me to the WhatsApp number given below. Subscribe, and thanks for watching.